In a typical household network, the modem is usually the first network element receiving downstream data from the internet, and the last element transmitting the upstream data. Its function is easily understood. One port is connected to the wide area network, that is, the internet, and one port is connected to the local area network, which is usually the Wi-Fi and Ethernet router. The same data, but on two different lines. One can infer that it is a kind of data signal conversion. The cable or fiber optic modem is not the only device performing the modem function. Any network unit on Wi-Fi also has an internal element performing the modem function, even without being called explicitly as such. Data in the form of digital voltage signals internal to the network unit like a computer or a smartphone cannot be sent as is through air. A Wi-Fi TX/RX, that is, transmitter and receiver, converts the digital voltage data into a certain physical form for Wi-Fi transmission through space, and vice versa. This conversion is a common paradigm in electronic communication technologies. The same principle applies to, say, Bluetooth or near-field communication. The term modem indicates a physical device, but more fundamental is the underlying concept, modulation and demodulation, which is the theme for this lab assignment. In order to understand the concept of modulation-demodulation function, it is relevant to have a broad perspective of the physical basis of modern communications. For the vast majority of electronic communications, the data are carried by the electromagnetic waves, which can range from radio frequencies to microwaves to light waves. Among the most iconic images of electromagnetic wave communications in daily life are the cellular towers, which, to the typical phone user, also represent the gateway link to the internet. Beyond the carrying capacity of microwaves, less visible than the cellular towers, but carrying the bulk of global internet traffic are light waves in optical fibers crisscrossing the continents and oceans. Regardless of the type, an electromagnetic wave is called a carrier if it is used to carry data. Consider an analogy. An airplane is a carrier, as it can be used to carry passengers. However, a pure electromagnetic wave as shown here, is like a flying empty airplane. The electromagnetic wave travels, but carries no data. For the data to travel, the data must be encoded on the wave like passengers boarding on a plane. The data encoding, which alters the originally pure sinusoidal shape of the electromagnetic wave, is called modulation. The reverse process to retrieve the data from the wave, like passengers getting off the plane at the destination, is called demodulation. There are many formats to modulate a carrier wave. Shown here is one of the simplest format known as amplitude modulation, or AM, as in AM radio. Suppose we wish to send a message consisting of two ASCII characters, H, I, for high. The digital waveform is a sequence of square pulses representing bit 1 or bit 0 as shown. The airwaves do not just containing the transmission of our message, because there are many other devices also busy in communicating. All messages arrive and cumulatively add together at the Wi-Fi router in this illustration. In fact, why does the radio or TV channel tuner is needed? Because the airwaves are filled with many broadcasting channels simultaneously at any moment. Without the channel tuner, the radio or TV will show the total mix of all broadcast programs at the same time. This is an example of interference, the communications that overlap in space and time with the specific channel of communication of our interest. Besides interference, there is something else that is always there in any channel of communication. Noises. Noises often show up as statics, whenever the communication signals are weaker than the noise power. Hence, communications always involve with interferences and noises. For simplicity, in this work, interferences and noises will be simulated with the random amplitude square waves as shown. This is not typical shot noises, thermal Johnson noises, or 1/f noises that are common in electronic communications, but it is sufficient to illustrate the concept for the educational purpose. At the receiver, the intended signal and the interference and noise are added together. Can the original intended message be retrieved from the net signal at the receiver? The answer is no. Consider this audio example with increasing noise.
Can you hear me now? Can you hear me now?
Real-life electronic signal transmission between 2 points is like two people trying to talk to each other across a loud stadium. Like the audio example, the message above is hopelessly lost. There is one technique that can solve this problem. Consider this analogy. A new coach goes to the field to meet his team for the first time. There are many kids there. He only knows the team's name is Roaring Lions. If you are a roaring lion, wave your arms. He tells the kids. A number of the kids do, and he knows who are on his team. Consider a signal with square pulses, like a group of kids. One way to make the signal to wave its arms, so to speak, is to impose a sinusoidal signal on its. This is called modulation. A pure sinusoidal signal that is used to carry data is called a carrier. This example shows a carrier frequency of 1 kHz. The clicking on/off of the AM, or amplitude modulation function, shows alternately the pure carrier without data and the modulated carrier with data. The following shows an experimental demonstration of the repeated message shown here, "Hi," being put on a sinusoidal carrier. By multiplying the signal with the sinusoidal function, the signal is comprised with both the message that consists of on and off square pulses, which are in turn carried by a continuous, steady sinusoidal waveform. Zooming in time scale to see the sinusoidal carrier. Zooming out for Fourier transform, click FFT. If you have learned Fourier transform, the bottom graph shows the Fourier spectrum of the modulated signal, indicating that it indeed has a frequency of 9.3 kHz, which is the chosen frequency. This method of modulation is called amplitude modulation, or AM, as in AM radio. Consider the modulated signal with added simulated noise. The noise amplitude is slowly increased. The signal plus noise appears random. However, one can still distinguish the signal from the added noise based on the carrier oscillation. As shown, what is needed is a circuit that can separate the portions of the total signal with carrier, encircled with red dash, from those without. The circuit that can do this task is the high-pass filter studied in Lab 6 Part A. As a function of the input frequency, its output is attenuated at low frequencies, but is largely the same at high frequencies. The noise simulated above has its main frequency band around few hundred Hz. Hence, the noise will be heavily attenuated. The intended data have a carrier of 9.3 kHz, hence, the data will pass through. This is the intended application of this Lab 6 circuit. This is an example of a high-pass circuit, which is quite simple. More details are given in Lab 6 Part A video. The signal plus simulated noise will be passed through the high-pass filter circuit. The filter output is monitored with scope channel 2 in blue. The random up and down noise is largely gone, only the signal with carrier remains. The main effects of the noise with abrupt level changes are the spiky oscillatory step responses, that was studied in Lab 6 Part A Step 3. This spiky behavior is inevitable and harmless, as it will be eventually filtered out by the demodulator circuit later. However, if a more conventional filter is desired, there will be an option for a flatter band top as discussed in Lab 6 Part C. This is a zoom in to see the filter performance. Even as a noise step vertically splits a data pulse into two, the filter passes the data pulse largely intact with just a step function spike. In the frequency domain concept, If you have learned Fourier analysis, the spikes represent the noise high-frequency spectral portion that is passed through by the filter. The higher the noise fluctuation is, the higher is the spike. However, what matters is the spike's total energy relative to that of a whole data pulse. Hence, as it will be shown later, when the filtered signal is demodulated, the spike's total energy will be spread over the entire data pulse duration and its effects will be largely imperceptible, except for a statistical increase of what known as the bit error rate. In the previous step, we use a high-pass frequency filter that selects signals with high-frequency carrier, but will that works if the interference is not low-frequency noise, but other communication channels with high-frequency carrier also? This illustrates the addition of another communication channel with modulated carrier to our data channel. As evident, in this case, the high-pass filter output appears to still contain both channels. It does not filter out the data of our interest while blocking the interference data, like the way it blocks the noise in the previous demonstrations. The reason is simple. The interference data has its carrier frequency, in this example, around 40 kHz, hence, both the signal of interest and the interference can pass through the high-pass filter practically intact. What is needed is a filter that allows the low-frequency signal of our interest, but blocks the high-frequency interference. In other words, a low-pass filter. This circuit, on the rightmost of the photograph, will take the signal and interference input directly from the adder circuit that is not shown. We need not be concerned with details of the circuit at this point. It is sufficient to say that, given a complex signal, the circuit selects the portions of the signal that have low frequency oscillation, and greatly attenuates those that oscillates at high frequency, which is the interference in this case. The signal plus interference will bypass the high-pass filter on the left, and couple to the input of the low-pass filter on the right. Unwanted connections should be removed. Scope channel 2, the blue cable, will be connected to the output of the low-pass filter. The low-pass filter output, the blue trace now shows largely the data of interest, and the interference is greatly reduced. The data with 9.3 kHz carrier passes through, while the interference data with 40 kHz carrier is greatly attenuated. This is the intended function of the low-pass filter. Both filters, high-pass and low-pass, are needed to reduce both noises and interferences. Connected together, they form a bandpass filter. Obtaining the response function of the combined circuit is quite straightforward. It is the product of the two response functions. On the log scale, a product becomes a summation. Hence, on the low frequency side, as the low pass response amplitude is 0 dB, the total response is simply that of the high pass slope. On the high frequency side, the response of the high pass is 0 dB, hence the total response slope is that of the low pass. The net result is a filter that blocks both high and low frequencies, allowing only a middle frequency range, hence, it is a band pass filter. Regardless of the detailed shape of a band pass filter, its main function is to pass through the desired data channel that has the carrier frequency in the pass band in the middle, and attenuate both noises and interferences outside the pass band. In the follow, both high-pass and low-pass filters, which are the circuits in the middle and on the right, will be connected together to make a bandpass filter. The data channel plus the noise and interference is coupled into the high-pass, which is the circuit in the middle. Then, the high-pass filter output in the middle, is coupled into the low-pass filter on the right, with a jumper wire. The bandpass output now shows mainly the signal of the desired data channel, with little remnants of the noise and interference. The data signal appears intact, while the interference and noise signals are reduced to spikes. To identify the signal sources, the follow shows the bandpass output for signal alone, or for noise and interference alone, or for both signal and noise and interference. Noise and interference is turned off. Output shows only the desired data signal as expected. There is a little resonance amplification, which is the property of this particular filter design. Signal is turned off and on. Only spikes remain as noise and interference are largely attenuated. The bandpass filter performs as expected. The last step is to simply demodulate the signal, that is, to remove the carrier from the original message. The demodulation is done in the simplest approach with a diode to make the carrier oscillation unipolar. Then the high-frequency component can be simply removed with a low-pass filter, to restore the message signal back to its original form. The process is now complete. The modulator output displays the digital message, high, as discussed above. The effect of noise and interference is a degradation of the signal, which is noisier, that is, its amplitude displays larger random fluctuations. Hence, the ratio of signal power, relative to that of noise and interference, also known as signal-to-noise ratio, is an important figure of merit in a communication link. If you have learned Fourier transform, use the FFT function to look at the signal spectra. There are two peaks, one at 9.3 kHz, corresponding to the desired signal, and the other at 40.7 kHz, corresponding to the interference. Observe the signal and the noisy interference taking turns to be on and off. When the interference is off, the demodulated signal pulse amplitude has little fluctuations. With the noisy interference on, the signal displays larger fluctuations. Part of the problem is that this filter is not sharp enough. Shown here was another project for a different class which uses a fourth-order, 8-pole filter that offers higher out-of-band rejection. The more discriminating a filter is, the less noise power can get through, and the better is the signal quality. This is the end result, the retrieval of the original message. In summary, this bonus project involves two additional circuits. One is to simulate signal and noise and interference. The other is to demodulate the AM signal. While the high-pass and low-pass circuits are the core of Lab 6 assignment, the basic tests of frequency, step, and impulse responses done in Part A, B, and C are essential but not significant in the broader context of applications. The true meaning of these circuits is the performance, such as in the simple AM modulation and demodulation demonstration. This circuit gives an output that is the negative sum of two input voltages. One input will be the simulated signal of interest. The other is to simulate noise and/or interference signal. The output will be used to test the filters. The input simulation can be obtained from the DG-Lent AD2 waveGen outputs. Use the modulation option, and AM or FM can be selected. Custom waveform for modulation can be imported as shown if necessary. As an example, this is the setup for the demonstration shown here. On the left, waveGen channel 1 simulated the digital message signal with an imported waveform for the AM function. As mentioned, the message was the binary ASCII code of 2 characters, H and I for high. The carrier frequency was 9.3 kHz, which is within the filter passband. On the right, channel 2 simulated a noisy interference signal. Since the filter in this lab is only second order, it is not a sharp passband and hence, a high carrier frequency such as 40.7 kHz was needed to be cut off. The built-in noise waveform was used for AM at a low frequency outside the passband also. Shown here is 379 Hz, which is comparable to the transmission rate of 140 bits per second of the channel 1 data. The demodulator circuit is designed as simple as possible, while at the same time, can help reinforce the learning of Lab 6. Here it consists of two simple elements. The first element is a single diode rectifier to make an AC modulated signal to become unipolar, hence having a DC component. The second element is just a low-pass filter designed at the signal baseband, that is, the data bit rate to extract this DC component. In common practice, a signal AC power detector, such as a nonlinear mixer on the left, would be best to use to detect the bandpass filter output to demodulate the signal. However, such a device is not included in your electronic kit. Hence, one can use a simple diode as shown on the right, which simply rectifies the positive portion of the signal voltage, so that the signal has a DC level, which can be extracted with a baseband low-pass filter. This video illustrates the diode rectifier. Blue wire scope channel is connected to the output of the diode rectifier. Scope channel 1 monitors the input of the diode rectifier. On the screen the yellow trace is the input, before the diode, and blue is the output, after the diode. The scope scale is changed to zoom in the signals for details. Note that the yellow trace is bipolar, whereas the blue trace has only positive side. Here, the blue trace shows that the diode output has only the positive component of the input, minus the contact potential of approximately 0.6 volt. Although this reduction of the signal by the contact potential is a slight disadvantage, as long as the signal is in the level substantially above 1 volt, this approach serves the purpose of demodulation application with the advantage of simplicity, using what available in the electronic kit. The output of the diode rectifier is coupled to a low-pass filter designed for the signal baseband of few hundred Hz. Note that this is a typical flat band design, with the roots as shown having sufficient damping coefficient. Building the circuits and demonstrating the whole process of signal and noise modulation, bandpass filtering, and demodulation, constitute the bonus project. One should note that this circuit can do more than the simple AM demonstration. See the video on FM demonstration for example. Hence, although the circuit is simple, it is a useful tool for an introductory learning of these subjects in communication engineering. It is hoped that this highly simple, modest lab exercise can offer the beginner an entry-level learning on the topic of signal modulation. Recall the analogy. A pure electromagnetic wave with constant amplitude, frequency, and phase is like a flying empty airplane. For a carrier wave to transmit data like passengers on an airplane, modulation of the wave properties is necessary. An analogy is to think that the different modulation approaches is like different ways to board and pack the passengers. The same data can be transmitted with different modulation formats. The same passengers can be seated differently on a plane. The objective is how to transmit the data most efficiently given the technologies available for the application environment. There are numerous modulation techniques, examples are shown here. Remarkably, many can be demonstrated for learning with this circuit, provided an expansion of the DG-Lent AD2 software package for additional capabilities. See this video for additional examples with frequency modulation.